Hello everybody, I am pleased to present the paper titled An Efficient Tool to Determine SU of Soft Soils. The outline of this presentation: first, an introduction about soft soils, then introduction to the cylindrical shear tool. Then we will present the reconstitution of Tunis soft clay, and we will detail the testing procedure using the CST. Then we explain and detail the determination of the undrained cohesion, obtain results, and their discussion follows, and we will conclude with some further development of this work. In introduction, we know that the characterization of soft soils, typically clays, inform that those soils have a very low permeability and their structure is colloidal and compressible. In terms of resistance, the undrained cohesion controls the shear strength of soft soils. And also, when sampling soft soils, we face soil disturbance, and as such, when we to test those soils, for example, to determine SU, we may have unravel determination. About experimental works on Tunis soft clays, there were a lot of development dealing with characterization, improvement techniques, and also constitutive modeling. So numerous investigations were performed since 1996, and the development in relation of this presentation is about the method of determination of the undrained cohesion. So for the vein test, we suggested a method to limit the determination of SU and the range of small deformation, which is applicable to all soft soils. And about in 2012, 2013, there was a new idea for measurement of the undrained cohesion of soft soils using the new tool we will be presenting. This tool, named Cylindrical Shear tool, is a vein hollow cylinder with sharpened tip. So here we have the sample, and we will place the CST on the soil sample. Then the first step, we will apply a downward vertical displacement, and we will have a small penetration D0, and then we will start the shear phase by penetrating at a prescribed rate of displacement this CST and the soil sample up to a final value of the penetration DF. About this cylindrical shear tool, the components are, as we can see here, one is the full tool, but it comprises the hollow cylinder we can see here, 2, and a piston, 3. Then the piston 3 itself comprises an annular ring, 4, here, the annular ring, and a headless socket screw, 5. And the annular ring itself comprises an inferior disc, 6, which you can see here, and a superior or an upper disc, 7, that you can see here. We manufactured two sizes of the CST, or two models. One is the big size tool with a height 100 millimeters, the inner diameter 60 millimeter, and a small size tool with height 70 millimeter and inner diameter 35 millimeters. Here we are presenting the reconstitution of Tunis soft clay. So when we reconstitute the soil, it is poured in, we fill the consolidation cell up to height of 45 centimeters, inner diameter 19 centimeters, and this reconstituted soil is subject to consolidation stress up to 30 kPa, gradually, of course. In this table, we see the physical parameters of the soil we reconstitute during this work. And on this column, we see the properties of the similar soil we reconstituted earlier in 1999. As we can see here, the total unit weight of reconstituted soft clay is about the same, about 60.6 to 17 kilonewton per cubic meter. And water content is about 51. And then there's small difference between the liquid limit, plasticity index, and so on. But it's very, very soft soil. The classification of the sample we used is here, which means it's out a high plastic soil. Now, to obtain the sample we will use for testing from the consolidated Tunis soft clay and the consolidation cell, we have three portions. We cut it in three portions: portion 1, portion 2, and portion 3. And we will show the location of the CST test we performed on those portions. So, for example, on portion 2, we performed a CST test using the big size tool here, and 2 using the small size tool, as you can see here in red, and so on. So we can see that we performed 1, 2, 3, 4 tests with the C using the big size tool, and about 8 tests using the small size. While for portion 1, we did not perform the CST test. Here we see the equipment we used. So as we can see, the sample portion we got from the consolidation cell, that is 1, and the loading frame we used, the loading frame of the triaxial apparatus. 3 is the load cell we can see here to measure the force, which is the reaction of the soft soil when the CST penetrates in the soil. And 4, it's a displacement transducer to measure the settlement or the displacement of the soil at upright. And as we can see here, the rate of penetration of the CST corresponds to the undrained shear. That means a high rate of penetration. To determine the SU, first we can remind that from the direct shear test we used the resistance between 2 soil portions. So the shear strength we measure, it's a soil to soil failure. This is a failure between parts of the soil. But while using the CST, as we can see here, when the CST penetrates the soil, we measure the resistance between the soil and the CST itself, the tool. So when the penetration is D of the tool, we can express the sheared area of the soil, and of course the measured resistance is the SU, since the soil is without friction, it's not frictional. Here we can see from the test we performed using the small size tool on the 3rd portion. So we have the variation of the recorded force when the CST penetrates the soil up to some value of the penetration. Of course, the more the penetration is, and the more the soil resistance is. But just to explain here which point we will consider to determine the ultimate force P. So as you can see here, it is in between this linear portion of the curve and the nonlinear portion. And we have also the ultimate penetration. And using the shear area expression, the SU is determined by this equation. In this table, we summarize the obtained SU by the CST and their average value, and we compare those values with the undrained shear, the undrained cohesion by the direct shear test. Here we have the relative difference between those values, or in another way, the ratio between the SU measured by the CST to that measured by the direct shear test. And as we can see here, we have some difference between those values, and we have the total average value of undrained cohesion, which is 9.8 for the SU and 9.9 for the direct shear test. So the relative difference is small, but in this case the relative difference is a bit high. In this graph, we have the comparison between the measured SU by the CST to the triaxial test, to earlier results we obtained, and the results by the direct shear test. So we can say that overall the measurement of the SU and for this tool soft clay is about satisfactory, because the difference between compared to the determination by the CST, the direct shear test and triaxial is acceptable. In conclusion, we presented a novel tool for shear strength determination, which is the CST. The merit of this apparatus is to avoid the soil disturbance, which gives a reliable SU determination. The experiment we performed, we considered two CST models, and we reconstituted Tunis soft clay, and we performed a test using the CST. Also, we suggested a new method to determine the SU and the measured undrained cohesion on dependent length of the CST model diameter, and the assessment of CST test results. We considered the comparison with direct shear and triaxial test, and this assessment gives encouraging results. And the recommendation now, of course, is to perform other tests, which is in progress, and we need further assessment. And finally, we mentioned that we can extend the CST tool to determine the shear strength of other type of soils. Thank you very much.